Okay. So in the previous two classes, in the previous yesterday's class, we talked about how to evaluate these various matrix elements. Okay, and we saw that, for example, if you look at the position operator and the momentum operator, they have their matrix elements are off diagonal. So if you calculate, for instance, the expectation value of the X operator in any moment, in any this eigenstate of the number operator, you will always get 0, because the matrix elements are off diagonal. So if you calculate, where is it? Yeah, so if you are basically looking at the diagonal elements, they are going to be 0. So if I write that down, right, all the elements of this form are 0. And now let's see. So what we want to do now is we want to talk about so we have these so we want to write down states. So first of all, we know what the form of the ground state is, right? We have already seen that the ground state satisfies this equation, right? This is the equation for the ground state. And what is this A dagger? X prime minus I P prime, right? Where X prime and P prime are the rescaled momentum and position operators. So you can write this as X bar minus I H bar D by D X prime. And well, this just becomes X prime. So if you ask what is the equation that is satisfied by the ground state, psi naught X is 0. Okay, and this equation has a solution which is a Gaussian. Right, so this is called a Gaussian, also known as a bell curve, right? Because it looks like an inverted upside down bell. So now one can also go about calculating expectation values in the old-fashioned way. That is that, let's say you have a system in some state psi of nx. Now, keeping in mind that psi of nx is not the state, okay? These are the coefficients of the state, but that's okay. Once you know what psi of nx is, you can calculate the expectation value of, let's say, the position or the momentum or any other operator. And I'm putting the subscript n to indicate that it is the expectation value of x or p in the nth state, right? So rather than going and looking at such a term, this is the same as, let's say, writing down psi of n x psi of n x dx, right? These two expressions are identical, right? because the nth eigenstate is right. This is the position representation, eigenstates. These are the eigenstates of the position operator, and these are the coefficients. So if you substitute this expression into this, you will get this expression on the right. Right. So both of these are okay. So, and again, the answer that you will get will be the same. You will just get, if you calculate x in the nth state with p in the nth state, you will get 0. So now to do this calculation, right? To do this calculation, you can either do this, right? So what would you do? You would insert the solution for psi of nx, and psi of nx is what? Psi of nx is some constant exponent alpha x squared, where alpha is some again that m omega by h bar or something like that, times h of nx, where h of n is the Hermite polynomial of order n, right? So what you would do is you would substitute this expression into this integral, right? And then you would so you would have two Hermite polynomials, one from here, one from here, and then multiplied by x, and then integrated over from minus infinity to infinity. So you can imagine that how tedious that process would be just to calculate this. On the other hand, one can just use the fact that x again x prime is a dagger plus a by 2. If you just use this fact, and then the expectation value of x in the nth state just becomes the expectation value of this guy, right? And this expectation value is easy. It's trivial almost to calculate, right? This is 0. You can see it's 0 directly, right? Because if you take expectation value of a acting on n will give you n minus 1. Inner product of n and n minus 1 is 0. Same thing for a dagger, right? So this algebraic operator based approach is much easier to deal with, right, than the approach based on the differential equation. Okay, so now one can similarly calculate the expectation value of x squared and p squared, and what you find is that these are not 0. Okay, so this I had given you for the homework, right? And I had asked you to do it for some particular state. You can evaluate these in the nth eigenstate, and you will also see that they are not 0. So once we can find these quantities, we can also calculate delta x. Now delta x is what? It's the uncertainty, right? So for delta O for any operator, what is it? It's square root of this expression, right? So expectation of O square minus square of the expectation of O, right? And so for the momentum of position operator, for instance, I have this becomes x squared minus mean of x squared. And the mean of x is 0, right? And if you calculate the expectation value of x, what will happen? Of expectation value of x squared, what will you get? Well, you can look at this. You can look at the form of this this bell curve, right? And you can see that if you calculate the average value of x, you will get 0. But if you calculate the average value of x squared, you will not get 0. You will get something positive. For the same reason, and by the way, this is for the same reason, the momentum operator will also will also, the squared of the momentum operator will have a non-zero expectation value. Okay, and so again, so this is homework number 5.3. Calculate this delta x, delta p in the nth eigenstate, right? The number operator eigenstates, right? And when you do this, what you will find is that delta x times delta p and delta x n delta p n will come out to be equal to h power by 2. Well, no, not h power by 2. It will come out to be equal to h power times n plus 1/2. Right? Now you can see that for n is equal to 0, this delta x, delta p is equal to h bar by 2, right? So what does this do? This saturates the Heisenberg bound, right? It saturates the Heisenberg bound, right? What is the meaning of saturate? Means that if you have any inequality, like this is an inequality, right? So if you say that it saturates, this inequality is saturated, that means you're looking at this condition that delta A, delta B is equal to C, because you have greater than or equal to, right? So the limit is when the equality is satisfied. So when this Heisenberg bound is saturated, right? So these are minimum uncertainty states, right? You cannot get states which have lesser uncertainty, right? So what we know now is that the ground state saturates this bound, but the other states don't. Excited states don't, right? So now one thing is that we would like to ask is what is it possible to construct states which will saturate this bound in a way that you know, like which is, so that we can describe something other than just ground states. Okay, and so states which satisfy this criteria, they are called coherent states. So these states saturate the Heisenberg bound. Okay. Now let first define what these states are. Okay. So these states are eigenstates of this destruction operator, right? A is the destruction operator. So for any operator, you can ask, what are the eigenstates, right? An operator has some matrix representation, right? And so you can always ask, this matrix will have some eigenstates and eigenvectors. What are those eigenvectors and eigenvalues? What are those eigenvectors and values? So here alpha is some parameter, right? And we will see in a minute what are the eigenvalues. Okay. So the simplest solution that we already know of is the ground state. So here alpha is 0. So the ground state is a coherent state with eigenvalue 0, right? Now let's look at some properties of these coherent states. Okay, so again, we don't need to. So first we can ask, well, what is the, if I write this alpha, right? It is some state. So if it's some state, then I should be able to again expand it in terms of the number operator basis, right? And what is this coefficient Cn going to be? Well, to find Cn, so what is Cn? It's just going to be n alpha, the projection of alpha onto n, right? So I can take this expression and I can put n on the left, right? And on the right, I will get alpha n alpha, right? And what is this n alpha? This is Cn, and I should write Cn as a function of alpha. Okay, so this is a an equation for my Cn. Okay, so but we still have not determined. We will see how to solve this later. But before we do that, let's look at some properties of these states. And we will see why they are called coherent states in a second. So some of the properties of these states. So we can calculate, for instance, the expectation value of the Hamiltonian, that means the energy. And what is this? This is going to be alpha h bar omega a dagger a plus 1/2 alpha, right? And now what is in the first term in the right hand side, I have alpha a dagger a alpha. What is this going to be? This is a of alpha is just this expression, right? And what is this bra of a dagger? Well, that's just the complex conjugate, right? So I can write what this becomes: alpha times alpha. Alpha. On the left also I will get an alpha only, right? Get alpha conjugate, alpha, alpha. Okay, this gives me modulus of alpha squared, okay, times inner product of alpha. And again, taking these states to be normalized, we have This is just equal to alpha squared. So then what is the expectation value of this Hamiltonian operator? A dagger A will just give me alpha squared. This will just give me 1/2. And so I can write down that H is equal to expectation value of H is equal to H bar omega into alpha squared plus 1/2. Okay. All right. Now, let's see. Right. So we want we still don't have a proper definition of what these states look like, right? So let's try to understand what it should be. Now you remember the completeness relationship, right? Completeness relation. Anybody remember what the completeness relation is? What is the completeness relation? If I have a complete set of states, like for instance, the number eigenstates, then if I write down this object and take a sum over all of the eigenstates, what do I get on the right side?
1.
More specifically, I get the identity matrix. Right? So I can use this to write down for any state, right? I can insert this condition like this, right? What am I doing? I'm just saying that the state is equal to identity multiplied by the state, right? 1 multiplied by some number, 1 multiplied by something gives me the same thing now. In this case, the identity multiplied by the object. And that is written in this way. Okay. And so now let's take this whole expression and right. Right. So now we go back to the previous expression I remember, right? And I said that, well, this C of n is equal to this n alpha, which is equal to this expression. Okay. So now we can use this expression, copy and paste. All right. We have this quantity, right? It's the same. We want to calculate this quantity. So if we can calculate this coefficient, right, then basically it will give us an expansion of alpha in terms of the eigenstates. So on the left, what you get? On the left, you have this guy, n acting on A, right? N acting on A is what? It's the Hermitian conjugate of A dagger acting on N, right? So because if I take the Hermitian conjugate of this, I'll get this expression, right? So on the right, I get root n plus 1, this Hermitian conjugate, and this will give me n plus 1 times root of n plus 1. Okay. And so then I substitute this expression back here, right? And I get n plus 1. I can bring the root n plus 1 out because it's just a number contracted with alpha, which is this expression, right? And on the right, what do I have? I have alpha n. Okay. So what does this give me, right? What is this quantity? This quantity is Cn, right? It's the coefficient of alpha in the number basis, n basis. And what is this? This is C. So this is C of n, and this is C of n plus 1, right? So this gives me a recursion relation. So now I can take n. I can start from any value of n, and I can keep going down by one level, right? So for example, if I reduce n, if I go to the next level, what will I get? Alpha n minus 1, right? So n of alpha is equal to alpha by root n minus 1, and this is the recursion relationship we need. And using this, we can calculate all of the Cn's, right? So now I just keep substituting for n minus 1, then n minus 2, n minus 3, and so forth, right? So I'll get n alpha is equal to alpha by root n. Then I'll get alpha by root n minus 1. Then I'll get alpha by root n minus 2. And this will continue, right? Until I get alpha by 2 times 1 alpha. And finally, that will become equal to alpha by 1 times 0 alpha. Right? So ultimately, all of the coefficients, all of the Cn's can be written in terms of a single coefficient, which is C0. And we can compress this notation a little bit. What will we have? How many powers of alpha will we have? We have 1, 2, 3, right? We will start with, so we'll get alpha to the n. And then in the root, we have n factorial. Zero n. Okay. So we have found a nice, again, this is all algebraic. We have not had to solve any differential equations anywhere, right? So you just start with, if you just go over this expression again, we just start with this guy, right? We start with the eigenvalue equation. We contract on both sides with n. On the right side, I get Cn alpha. On the left side, I get A acting on n. A acting on n gives me root n plus 1 times bra of n plus 1. This gives me a recursion relation, right? Connecting n and n plus 1. I can write this recursion relationship in terms of n and n minus 1. And then keep substituting until I get this. All right. So then finally, I can write down the expression for alpha. What is the expression for alpha? Alpha is simply Cn times n, right? And what is Cn? Cn is alpha n by, okay, now I'm at the end of my screen, so it's, yeah. So now I can write alpha as 1 to infinity. And what is Cn? Alpha n root of n factorial and this is just a number, right? So I can pull this outside. It's better to write it over here. And so this is my expression for the coherent state in terms of just one quantity. Which quantity? The zeroth coefficient. But I don't have the zeroth coefficient, okay? So then the question is, how do I determine this zeroth coefficient? Now, in order to determine this zeroth coefficient, we need a little bit more. We need to introduce one more thing. Okay. Green. We need to define something called a displacement operator. Okay. Now, what is this displacement operator? This displacement operator is defined as follows. It says that if you take the ground state 0 and you act on this with this operator, you get alpha. Okay. I mean, this you can do for any two states, right? For any arbitrary pair of states, let's say alpha, if you have for an arbitrary pair of states, for any two states, alpha, beta, we have some operator, right? Some operator O, right? There exists some operator O such that alpha is equal to O times beta, right? This is just a obvious statement, right? So we are saying that we take this ground state and we define some operator such that the action of this operator on the ground state gives me alpha. Okay. And then we will look at the properties of this alpha and we will see that it has all sorts of nice properties. Okay. So first, so let's ask what are the properties of this operator. Okay. So first of all, do you guys have another class, by the way, now?
Yes, sir.
Yes,
Huh?
sir.
Yes, sir.
Okay, okay. That's why people are leaving. All right. So I should stop here. Right. We'll continue tomorrow. I thought that you didn't have class till 11:30. So. Or till sorry, till 10 o'clock. Okay. So any questions? It's all been fairly straightforward, I think, right? So this all of this actually shows the beauty and elegance of this Dirac notation, right? Because if you didn't write things using these Bra and Ket vectors, you can see how complicated your expressions would become. Every time, for instance, you have to write an inner product, right? You would have to write something like sum over some index, then the sum over the, so if you have inner product of UV, right? So the Dirac notation is basically just like the vector notation. Rather than saying U of I, V of I, sum over I, in the vector notation, you say U vector dot V vector, right? And so this is just a generalization of this notation to complex vectors, to complex vector spaces. And for complex vector spaces, you need to have a notion of this inner product has to be defined in terms of complex conjugation. So when I'm writing this something like this, what it is secretly is basically n complex conjugate dotted with alpha, right? That's what this expression means. But rather than writing expressions of this form, this is more suitable. Why? Because, for instance, if I write down this inner product, how would this inner product be written in that case? It is, you would have n this thing something times n transpose complex conjugate sum over n is equal to the identity. This is not the most elegant way to write it, right? But if you just write it like this, it's like a machine. It fits. You have these slots on the left and on the right. You can put something on the right. You can put something on the left. Right. Okay. All right. So the fifth. So we will have our first quiz on Tuesday morning, 8 a.m. Okay. And I'll see you then. So I'll